Great pleasure to introduce Immanuel van Santen, who is also my old doctoral brother, and who will talk about algebraic families of automorphisms and solvability. So, Immanuel, please go ahead.
Thank you a lot for giving me the opportunity to speak here at this algebraic transformation group seminar. So first of all, I have to say this is joint work in progress with Serge Cantat, Hanspeter Kraft, and Andriy Regeta. So my plan for the talk is quite, how to say, generic. So first I will start with an introduction. I will speak about the main theorem. I will give a lot of applications, and I hope that I can give then a rough idea of the proof in the end. So let me start with the introduction. So the setup is that we work over a field K, which is algebraically closed of any characteristic, and for the whole talk, X will be a variety which is defined over that field K. And somehow the main protagonist, I think, of the whole seminar is this automorphism group of the variety. So this is the group of algebraic automorphisms of the variety X. So the general philosophy is the following. Philosophy, at least a bit for me. So this group out X could be quite huge and difficult to understand. There's a lot of theory about algebraic groups, and the philosophy is somehow try to establish structure results for this group in analogy to algebraic groups. Okay, this is very vague, of course, but this is somewhat the general philosophy. Good. So, yes. Somehow a main example you can have in mind is the affine space. The behavior is also rather typical, at least for very symmetric varieties. So when the dimension is 1, then the automorphism group is an algebraic group. It is just the affine linear transformations over the field K. So these are the transformations of the form AX plus B, where A is a non-zero scalar and B is some arbitrary scalar. When the dimension is 2, then due to Young and van der Kolk, we have a nice theorem. In fact, this automorphism group is then an amalgamated product of the so-called Jonquière automorphisms and the affine linear group in dimension 2 over the intersection. So this Jonquière group consists just of the transformations of the form A1x1 plus B1 and A2x2 plus B2 of x1, where just with the A1 and A2 are non-zero scalars. B1 could be any scalar and B2 is some polynomial in x1. So this is a very nice structure, and this enables us to say a lot about the automorphisms of out A2. But when the dimension is bigger than 3, then structure of out AN is quite mysterious and we don't know so much. Okay, so this is just for that example. To start right away, I would like to define what an algebraic family is, what I mean with this. So an algebraic family of automorphisms. So for this, we take a variety A. So A is a variety. And then we look just at an A isomorphism, or at A automorphism, in fact, from A times X to A times X. So this means when we subject to A, then this diagram commutes. So such a phi is an algebraic family of automorphisms, which is parameterized by A. And this gives rise to a map from A into the automorphism group of X by sending A to the automorphism, which sends X to phi of A comma X. And in fact, such maps which arise from algebraic families, we will call morphisms. So this is a morphism. Okay, let me give a very important example. So let's say we have an algebraic group action on the variety X. So this is given by such a map. Okay, so this gives rise to a morphism from G to out X. So this is a morphism. And of course, it is also a homomorphism of groups. Okay, and just once and for all, I would call images of such morphisms, which are also homomorphisms, I will call algebraic subgroups. So the image is an algebraic subgroup, algebraic subgroup. And I will abbreviate this by algebraic subgroup ASG. Okay, good. So in fact, a small remark, in case if G is an algebraic subgroup of out AN, then G is of bounded degree. Okay, meaning that there is integer big K, let's say, such that every polynomial that appears in the automorphisms representing the elements of G is the degree of these polynomials is bounded by that integer. So for example, if I look at the morphism, which is also a homomorphism from GA to out A2, okay, where I send T to the automorphism X, Y plus Tx to the power K. So the image is of degree K. Okay, so far, so good. Another important notion for the talk will be the notion of an algebraically generated subgroup. So I will come to this in the next. So definition, a subgroup G in out X is algebraically generated if there is in fact a morphism rho from A to out X such that the following properties hold. So first of all, A is irreducible. Second, we want that the identity is in the image of that morphism. And third, of course, this G is generated as a group by this image. Okay, So this is the group generated by rho of A inside the group out X. Such a subgroup I will call such a subgroup I will call algebraically generated. Okay, let me give a short example here. So let's say X is again the affine plane, and I define HB as the following element of the Chantier group X, y plus bx to the power k. This is an element in the Chantier group, where k is just an integer which is bigger than 1. And S is just the element that switches the coordinates y and x. So some computation shows the following computation, that the degree of the composition of S with HB, and I iterate this composition n times. So this is exactly the degree of HB to the power n, and this is in fact Kn. Okay, maybe I should say here something that it is really true. I want that the B, of course, is non-zero. Okay, so with this, we can now construct some morphism. So let's construct this morphism as follows. Rho goes from A1 to out A2, and I map B to S composed with HB, composed with S, composed with HB. Okay, so this one is a morphism. Okay, and in fact, we see here when B is equal to, sorry, I should say the B non-zero, this is just meant here. Okay, so when B is 0, then this is the identity, and S is an involution. So we see that the identity is inside rho of A, also rho of A1. A1 is irreducible, and so the group generated by rho of A1, this is an algebraically generated subgroup. Okay, but it is not an algebraic subgroup. Okay, and the reason is that the degree is unbounded. So the degree is unbounded. Okay, good. There are, in fact, two other notions which will turn out to be very important for us. So let me introduce them now. So let's say G is some subgroup. So G is in out X a subgroup. Okay. Then we say G is connected if for every element in this group G, there exists a morphism rho from A to out X, okay, which is a morphism, okay, such that the following holds. So G and the identity are elements in the image, and rho really maps into the group G. So in some sense, this image of this morphism connects the element G to the identity. Okay, this is the notion of connectedness I want to use. And another very important notion is the notion of the dimension of a group. Could also be done for any subset. So the dimension of G, this is just the supremum over the dimension of A, where we run through all injective morphisms from A to out X with the property that the image is really contained in G. Okay. So a small example. Out A2 is connected. And this can be seen as follows. We saw that out A2 is a amalgamated product. So every element I can write as S1 composed with H1, composed with S2, composed with H2, and so on, until Sn with Hn, where the Si is an element of the affine group, and Hi is an element of the Junyi group. But we can also assume, because there are only finitely many elements, we can assume that these elements are of bounded degree by some integer, let's call it k. Okay. The point is now that both of these, okay, these are connected algebraic groups. Okay. So this means phi is in fact really inside the image of a morphism with an irreducible parameter variety. Okay, in fact, not with the same argument, but somehow with kind of, it's not so hard. One can also show that in fact out AN is connected as well. Is connected.
No, the Junyi less than equal to k, that will not be a subgroup, right? That's a subvariety.
Excuse me, I didn't understand.
No, you said that this Junyi group,
Yes.
degree less than equal to k, that's a subgroup. Is that a subgroup? I thought it will not be a subgroup. It will be only a variety. Because when you compose, you are going to increase the degree.
No, I think it's a subgroup.
No, because the point is, the point is that we are in dimension 2. When we are in higher dimension, then not, but in dimension 2, it is a subgroup. I mean, when I compose, I insert in the, in fact, I have my first Junyi element, and then I insert somehow a linear combination of the first coordinate in the next one, and then I add polynomial.
Oh, I see. Okay.
Also in higher dimension, I think it's.
But in higher
it's a
dimension,
subgroup.
you are completely right.
Yeah, okay. It's the dimension 2 phenomenon. Okay, yes.
I don't think so. I think in higher dimension, it's also a subgroup. I think it's a subgroup in any dimension. But
Okay,
anyhow.
depends of what you mean with less or equal than k. But we agree that on the in dimension 2, it's fine. Okay, so let me give another example for the other notion, namely for the notion of a dimension. So if G is in out X an algebraic subgroup, okay, then the dimension of G is finite, okay? So why is this the case? Let me give an argument for that. So, right, indeed. So for this, I have to take any injective morphism, let's call it rho, from A into out X, such that the image is contained in G. So this is an injective morphism. Okay. Good. So in fact, here, this G is an algebraic subgroup. So in fact, I have here an H, which is an algebraic group. And I have a morphism, which is a homomorphism into out X, such that the image is G. Okay, this is by definition of an algebraic subgroup. And then I have also this injective morphism, okay, we have taken before. And what we can do now is we can construct the fiber product of these two maps. over out X. Okay. And this is in fact because both are morphisms. This is something which is closed inside the product of A times H. Okay. So the injectivity here, this gives me the injectivity of that map here. Okay. And because the image of H is G, this gives me the surjectivity of that map here. Okay. So this means I have here a surjective map. I have here an injective map. So this gives me that the dimension of A is in fact bounded by the dimension of H. Okay. And the dimension of H is something which is just something fixed, chosen from the beginning. So we see that the dimension of G is really bounded. Okay. And in fact, for connected subgroups, the reverse is also true of this example. And this is a theorem due to Ramanujan. So I need a little bit more space. Let me do this. I'm sorry, I have just to move this slightly. So I take the theorem of Ramanujan from the 60s. And in fact, we generalized this also to the case when X is not necessarily irreducible. So G is in out X some connected subgroup. Then the following hold, we have that G is an algebraic subgroup if and only if the dimension of G is finite. Okay. And in fact, in this case, the G has a unique structure of an algebraic group satisfying some universal property. There exists a unique structure of algebraic group on G such that the following universal property holds. So I have here my morphism to out X. Okay. So G, and in fact, if I have any morphism rho to out X, such that the image of rho is contained inside G, I have a unique factorization through G. And this one here, this one here is really a morphism of varieties. Okay, so this is the universal property which is then satisfied by this structure of an algebraic group. Okay, good. So I introduced many things. So we come now to the second chapter. This will be the main theorem. So I start with an algebraically generated subgroup. So let G in out X be algebraically generated. Okay, and the question is, I also wrote in the abstract, under which conditions is G an algebraic subgroup? Okay, and there is a theorem which is due to Cantat, Regeta, and Xie, published in 2003. So in case if X is affine and G is commutative, then yes, okay, then the question can be answered affirmatively. Okay, and in fact, our main theorem is a generalization of this result. So Okay, this is work in progress, so from 2026. So if X is quasi-affine and G is not commutative, but G is solvable, then again, yes. Okay, let me give a remark for people who are also interested in birational transformations. So in a birational setting, the statement is in fact false. So in a birational setting, the statement is false. And for this, you can consider, okay, this is a morphism from A2 into the group of birational transformations of A2, where I send lambda mu to the birational transformation, to the following birational transformation. I send x, y to x and y plus lambda over x minus mu. Okay, so then in this case, A2, of course, is irreducible. The identity is in the image of this morphism when I take for lambda 0. Okay, so this means that rho of A2, this is in fact, this is algebraically generated. And in fact, it's also commutative, okay, but not an algebraic subgroup, okay? And the reason is that, in fact, in this group here, we have algebraic subgroups of arbitrarily high dimension. So this is then not possible. Okay, and one notion I want to introduce, because this is very good for the rest. So I call a subgroup G in Audix, I call algebraically tame. Algebraically tame. If G is connected, okay, and every algebraically generated subgroup is in fact an algebraic subgroup. Okay, so when we reformulate theorem A, we could say theorem A says that if X is quasi-affine and G is a connected solvable subgroup, then it is algebraically tame. Okay, so I will come to the promised applications. Applications. So the first applications concern the structure of connected solvable subgroups. So structure of connected solvable subgroups. Okay, so classically, when G is a connected solvable algebraic group, then we can write G as a semi-direct product of a maximal torus with U, and this U is a connected and unipotent. And in fact, it is equal to the set of all unipotent elements. And the first application of our main theorem is, in case X is quasi-affine, and G is connected and solvable, then we have somehow a similar decomposition. We can namely write G as a semi-direct product of maximal torus. Okay, so maybe I have to be here a bit more precise, where T is a torus of maximal dimension. Okay, and U is a subgroup which is algebraically tame. Okay, and it is the union of all its connected unipotent subgroups. In fact, we can say it is the union of all the connected unipotent subgroups of G. This is in fact true. Okay, let me give the proof of this corollary. So theorem A gives me that the G is in fact algebraically tame, as already mentioned before. Okay, so now for T we take just any torus of maximal dimension. So let T in G be a torus of maximal dimension. This exists because the dimension of any torus in an automorphism group of X is bounded by the dimension of X. So the dimension of T is always bounded by the dimension of X. Okay, this is not true for unipotent groups, but for a tori this is true. Okay, and I define U. For U I have no chance, so I have to define it as the union of all connected unipotent algebraic subgroups of T. Okay, in the statement I should say all the connected unipotent algebraic subgroups of G. Okay, so with this, of course, U is normal in G, and it is a subgroup. U in G is a normal subgroup. And in fact, the intersection with T is just the identity. Okay, so we just need that T and U generate the group G, and for that I take just any element G. So for all G in G, there exists a connected algebraic subgroup G, which is contained inside G with G in G. Okay, and then after enlarging my G, okay, I can assume that the torus of maximal dimension T is also contained in G, and thus we can write this G as in the classical case as T semi-direct product with some connected unipotent subgroup, and this yields then that G is really the desired semi-direct product. Okay. I didn't ask so far. Are there some questions? Okay, then I come to the second part of applications. So this is about Jonquière subgroups, Jonquière and Borel subgroups. So Jn, this is now the Jonquière group in dimension n. I think it is just similarly defined as for dimension 2. So I hope it's fine that I don't redefine it. So this is just the Jonquière subgroup. Okay. Good. And in fact, there is another characterization. I can say this one is the same as the stabilizer of the following composition of projections. Just I project to also a point x1 to xn, I map to x1 to xn minus 1, and then I do the same to an minus 2 and so on until a1. And the stabilizer, as the automorphisms that stabilize all these compositions of projections, this is exactly the Jonquière subgroup. So it's just another characterization. And Jean-Philippe Furter and Pierre-Marie Poloni proved that, in fact, this Jonquière subgroup in out AN is a Borel subgroup. Okay, so it is a maximal connected solvable subgroup, and the derived length of Jn is in fact n+1. Okay, and our theorem C. Okay, so this is the following. So if X is quasi-affine, and let's denote by n the dimension of X, okay, and G is in out X any connected solvable subgroup. Okay, then the following two statements hold. In fact, we can bound the derived length of G by n+1, and if the derived length of G is this bound, okay, then in fact X is isomorphic to AN, and G is conjugate to a subgroup of the Jonquière group. Okay, in fact, this theorem, this is a generalization of a result in a paper of Kraft and Seidenberg. So they proved it in case X is affine and the characteristic of K is 0. Okay. Maybe I say something about the proof strategy. So yeah, the proof strategy is as follows. Proof strategy. So we write first the G as we already saw in corollary B. We can write it as a torus semi-direct product with this U. And then in this case, the commutator is contained in U. Okay, so we can really work with U when we want to prove this theorem. Okay, and the key is, let's call key claim, is the following. If U acts on X with a dense orbit, okay, then
I'm sorry, I missed this dl of G. It's what? It's derived length?
Yeah, exactly. This is the derived length.
Okay, thank you.
Then X is isomorphic to AN, and this U is conjugate to a subgroup of the Jonquière group. Okay. And in fact, once having this key claim, the thing is quite fast. So for any x in X, we define ux in out ux. Okay, so this is the image of u in the automorphism group of the orbit of ux. Now this is the orbit. Okay. So the image of u. Okay. In this case, we have that the derived length of u is in fact the supremum of the overall points of the derived length of all these images. Okay. And in fact, now for proving one, okay, this is then enough to show the then we can work with this ux. Okay, ux acts in fact transitively on this orbit. Okay, and then we know that the dimension of this group ux, the derived length of this group ux is then bounded by the dimension of the orbit plus 1, and so we get by this here, we get then that the derived length of u, we get that the derived length of u is bounded by the dimension of the, the derived length of ux is then bounded by the dimension of the orbit. And so the derived length of u is then bounded by the dimension of x. And for 2, in fact, because we established 1, we know that then u has to act with transitively, that there is in fact only one orbit, and then it is a direct consequence of the key claim. Okay, so the key claim is somehow the main point how to do it. Okay, another funny application I would like to show is the following. So this is theorem D. So G is in out AN. This is connected and solvable. And G contains a torus of dimension n. Okay. Then in this case, G is conjugate to a subgroup of the Jonquière group. Okay. And the proof is, okay, I have maybe to make some decision. So maybe I leave out the proof. The main strategy is somehow one uses root subgroups. So first of all, we can assume that the G contains the standard torus, and then one uses root subgroups. Okay, and again, we use somehow that we can write our connected solvable group as this standard torus with this unipotent group U. Okay, another application concerns nested subgroups. So nested subgroups. So let me recall that a subgroup in out X is nested if G can be written as the union of Gi, where these G1 in G2 and so on, this is a increasing chain of algebraic subgroups. Okay. And our theorem here is as follows. So for a subgroup G in out X, the following are equivalent. So first of all, G is algebraically tame. The second statement is G is in fact a union of all G in S, where S, this is a directed set of algebraic subgroups. Okay, so this is a directed set under inclusion of algebraic subgroups in out X. And point 3 is G is nested by connected algebraic subgroups. Okay, so this gives also the relation of the term nestedness, which is somehow very popular and very much used. So this gives somehow the connection of algebraically tame and nested. So in fact, it is more or less the same. Okay.
Could you remind what is
Yes.
algebraically tame?
Yes, algebraically tame. This means that if you take any algebraically generated subgroup in G, it is already an algebraic subgroup. Okay. So our main theorem can be phrased as every connected solvable subgroup is algebraically tame. Okay. Good. So clearly, we can say when we have one, when a group is algebraically tame, I can take all its connected algebraic subgroup and then I can form my set S. So maybe I should say there exists, maybe I should, to be more precise, there exists an S such that the following holds. Okay, so this is the correct statement. So then we can define this set S, which is directed just by taking all connected algebraic subgroups. Okay, so 1 implies 2, and we have that 3 also implies 2. Okay, so if G is nested by connected algebraic subgroups, I can just take all these algebraic subgroups, G1, G2, G3, and so on. And this is directed, and of course, G is then the union of them. Okay, so let me say something about the proof idea here. So for the other implications, so this is really just a very rough idea. It's more kind of a strategy. So in fact, the G I can write as G. So this is a connected algebraic subgroup times some U. And in fact, this U serves as some sort of a unipotent radical, radical of G. Okay, and the point now is somehow this G here is something of a finite dimension, so that this doesn't hurt so much. So the main point is somehow to look for this U here. Okay, and the point is, in fact, there exists a U stable open affine x0 in X. Okay, also open affine, so maybe I should say dense. Yeah? Open dense affine x0 in X. Okay, and then we can in fact work with the image U prime inside out x0. Okay, and this out x0, because x0 is now an affine variety, this is in fact the so-called int group. Okay, and okay, there are somehow a bit more tools that one can use. So maybe for the existence of this open dense affine subset, one can say the following. In fact, due to a result of Popov, there exists, in fact, inside G, also inside this G here, I can find the image of a morphism coming from an irreducible variety where also the identity is inside, such that the orbits of this image are the same as the orbits of this group G. Okay. Now this G is algebraically tame, so in fact I can say this comes from an algebraic subgroup of G. So we can also do the same trick with this U. Okay, and so this gives me somehow connected algebraic subgroup. Okay, which has the same orbits as this nice written U. Okay, and then it's in fact just a result due to maybe, I don't know who is the first one who proved it. Maybe it's Matsumura who proved, at least it's in a paper of Brion, in some quite generality, that there exists such an affine U stable X0. Okay, I would like to give you also some example because I think this is quite interesting.
Good question.
Yeah.
Maybe I didn't get it correctly. You said G is algebraically term, mean whenever you take two algebraic subgroup, the subgroup they generate is algebraic itself.
If I take an algebraically generated subgroup, then it is algebraic itself, yes.
So in a different direction, let's say I consider all algebraic subgroup of G and ask whether they form a filtered system.
Yes.
I mean, if they form a filtered system, then I can take the filtered colimit and I get some in-group in a large interpretation with a map to G. Is your theorem kind of way of saying that under certain hypothesis, this map is an isomorphism? That you can extract a countable presentation by increasing inclusion from this abstract filtered colimit?
Yes, in theorem E, yes. In some sense, yes.
Okay.
Yeah.
Okay, thank you.
Okay, so I want to give you some example. So this is for people interested in positive characteristic. So let's say P is the characteristic of K, which is bigger than 0. Okay. And then we define Fn as the following map from Ga to the power n to Ga. So I define it via F1 is in fact x1 minus x1 to the power p, okay? And then inductively I define Fn plus 1 as Fn plus Fn to the power p to the power 2n minus 1 minus xn plus 1. Okay, so this is for all n greater or equal than 1. Yes. Okay, and now I define my un as and then of course when we see here this F1, this is in fact a homomorphism of algebraic groups, in fact from Ga to Ga. And this one here is just addition, subtraction, and so this is also a homomorphism of algebraic groups. Okay, so this Fn by definition is a homomorphism of algebraic groups. Okay, so let me define Un as the kernel of this homomorphism. Okay, so this is a subgroup inside Ga to the power n. Okay, and then we have that Un is contained inside Un plus 1 intersected with Ga to the power n times 0. Okay, so when we make xn plus 1 equal to when we make the last coordinate equal to 0, and we intersect it with the elements of un plus 1, then inside there I have my un. Okay, good. So we can define U as the union, which is an increasing union of these UNs. And this lives inside, let's call it GA to the power infinity. And I can realize this as a closed subgroup in out A2 just by taking the maps x, y plus p of x, where in fact p runs through all polynomials in x. Okay, this is in out A2. Okay, so by the construction, and this is the reason for the construction, is we have in fact the following. When we plug in fn plus 1, x1, 0, and then just zeros, okay, I get x1 minus x1 to the power p to the power 2n. Okay, good. So what gives me this? That when I intersect un plus 1 with GA times all the rest are 0, okay, then I get exactly f p to the power 2n times, and the rest is just 0, okay? And this is a subgroup inside GA n plus 1. Okay, so good so far. So far, so good. So if I intersect my U with this GA cross and here all zeros, okay, then I get in fact, and here I don't stop, so I always just take zeros, okay? I get in fact the algebraic closure of FP with where always I add here 0. Okay, so something funny happens now. In fact, if K is now FP bar, okay, then in fact GA, which I define just as this, this group here, okay, this is something which is contained inside U, okay, but this GA is never contained in UN. So for all n greater or equal than 1. Okay. So this is a phenomenon that is really particular to positive characteristic. This cannot happen in characteristic 0. Okay. And another application of our main theorem is the following theorem. So when X is quasi-affine and the characteristic of the ground field is 0, okay, now this is important, and U in out X is nested by connected algebraic subgroups, okay, then the conclusion is that this U is in fact in out X closed. Okay, so this means for all morphisms rho from A to out X, okay, the pre-image rho inverse of U is in A closed. So in fact, this is due to Perepechko in case X is affine. So Perepechko in case X is affine. And one remark I want to say is, in fact, if now K contains properly this FP bar, okay, in the example above, we have that the GA intersected with U, okay, which is just FP bar, okay, when we really consider this copy GA, okay? So then this intersection is really FP bar. So this is then properly contained inside GA, okay? So we see that then in this in the example, U in out A2 is not closed. Okay, so we see the theorem is false in case the characteristic is positive. So maybe I have to ask how much time I have. I think it's now roughly an hour.
Yeah, it's about an hour now, yes. So it's like if you have something to say, then please limit yourself.
Yeah, I mean, I have much more to say, but maybe I stop here and
Okay.
yeah, I thank you for your attention.
Thank you very much. Thank you for a nice talk, but now let me ask if there are some questions in the audience.
Yeah. So I have a question.
Yes,
So
please go ahead.
you gave us example of tame, if I understand correctly, the semi-direct product of an algebraic semi-simple group, say, and it's a solvable group, connected solvable. Yes. And now, do you know some example which is not of this origin?
Sorry, can you repeat the question? I don't fully understand. Want what kind of
What
example?
are your examples of tame?
Also my examples of tame algebraic subgroups. Or what?
Tame, not tame algebraic, just tame in your sense. Tame,
Okay.
Algebraical tame.
algebraically
yeah.
tame, yes. Not tame algebraic, but algebraically tame.
Yeah. So, I mean, if you have an algebraically tame subgroup, so this is the same as a group, which is a subgroup which is nested by connected algebraic subgroups. So this gives some kind of another.
Okay. This is just examples, all nested.
Yeah.
Not nested connected, nested connected. Okay.
Yeah, as a nested and yeah, exactly. Yes. Yeah.
Next. Thank you. Okay.
I just want to insist here and say, I mean, I speak here for all varieties, not just only for affines. And so I really want that just it is nested by connected algebraic subgroups. So this is just a statement we have.
Okay. Thank you. Okay.
Any further questions? Remarks?
There's a question
Okay.
of when the paper will be available.
This is a tricky question.
Tricky question, yes. Hopefully soon.
Okay, thank you.
Okay. Well, if there are no further questions, I'm not supposed to ask questions about this project. So if there are no further questions, then
You mean you are supposed to ask for answers, not for questions?
yeah, somehow I'm involved in this. So I mean, I have asked many questions about this already, and still we have many questions, but we don't know maybe how to answer all of them. Anyhow, thank you, Immanuel, for a nice talk. And
Thank you.
see you in 1 month. And in 1 month, Jen Freudenberg will give a talk. So there will be an announcement about this. So Thank you. And
Great. Thank you for the
Thank
organization.
you, Andriy, for handling the programmation and the reminder.
you are very welcome. Okay, thank you.
I wanted to say thank you for your talk, Andriy. It was a pleasure to me. Thank you.
Thank you.
Okay.